Okay. We're going to start today with kind of expanding on the spectroscopy. I put the problems where you're going to match the protons to the peaks in the 7 spectra. That's online and it's due by tomorrow night at midnight. So if you haven't already printed out your structure, you print out the spectra and the structures, match them up, and then go back online and just type in the letter for every set of protons. And then the computer will grade it, and what will happen is that on Saturday morning I'll release the initial score. And then probably what I'll have you do is, if you missed any, if you didn't get them all 100%, then you can go back and figure out which ones are wrong. You're not going to get, it's not going to be everybody gets 100%, but it'll be a certain percentage for the first time through and then a smaller percentage for the second time through. That way you can go through and see what you missed and try and figure it out. So it'll make more of an impact. But what we want to do is we ultimately want to get to the point of being given a spectra and trying to figure out what the compound is. And so far we've done matching, which is the best way to start. But what we want to do is to basically say, okay, here's my spectrum, then here's a with that. But the only way to do that is to really get more information. So part of this, we're going to go back and just quickly review what we've done over the last couple weeks, and then we're going to talk about more information that I can get that will be helpful. So in terms of our spin-spin couplings, these slides are just basically kind of a review of what was from the previous slides. And that is that, in particular, when you have what's called a geminal system, okay, in lecture, I've talked about geminal dibromides, where you have 2 bromines attached to the same carbon. If you have 2 hydrogens attached to the same carbon, that's what's called a geminal. And for the most part, these 2 hydrogens are chemically equivalent unless they're not. Well, there are some circumstances where 2 hydrogens attached to the same carbon would not be chemically equivalent, and therefore they would split each other. Most of the time, splitting comes from neighbors, but there are a couple of occasions. One of the best examples of this is, let's say that looked something like this. If you had this molecule, it would turn out that this A and that B hydrogen, because there's no mirror plane that you can cut the molecule in half with, that molecule, those A and B hydrogens would actually be not equivalent. And so in this case, it would actually be split by this one and then by the neighbor. So that this hydrogen would actually be a doublet by B and then a doublet over here. And this B would be a doublet from A and there. So you have to be careful that sometimes that will happen. In alkenes, it happens quite a bit. If you could imagine, if you had an epoxy, you had a CH2 on it, and those 2 CH2s weren't separated by a mirror plane, you'd have a similar situation. But for the most part, our couplings have just been from neighbors. But occasionally, they come from a geminal system. So we've already talked about the n+1 rule, and we've already talked about F peaks if you're in between 2 non-equivalent groups. So if you've got a CH2 on one side and a CH3 on the other, if you want to estimate the peaks, just add up the total numbers. And we've talked about Pascal's triangle in terms of that's what gives us a 1 to 2 to 1 triplet or a 1 to 3 to 3 to 1 quartet. And 2 protons that are coupled to each other, they have to have the same coupling constant, and the coupling constant is constant. It doesn't change as the magnet gets stronger and stronger. Now, there are some what we call complications to splitting. The n+1 rule doesn't always work. We've seen that coupling to non-equivalent protons. For instance, if you had, if you had a CH2 sitting in between a CH2 and a CH3, that this CH2 would then be really a triplet of quartets, or a quartet of triplets. And then if you really wanted to look at that in detail, you'd have to look at all the splitting tree, thing else. But what turns out to be a little bit more important complication to splitting is what is called non-first order effects. And that basically says that, you know, the doublets and triplets and quartets and even the doublet of doublets and doublet of triplets breaks down. Distance between two protons in chemical shift is less than the coupling constants. Actually, that's not true. There's a certain formula for that. But when the distance between the two peaks in terms of their chemical shift gets pretty similar to the distance between the peaks because of the coupling constant, the spectrum, in essence, just goes to hell. Predict what the splitting pattern will be, and I'll show you a couple of examples of that. So let's imagine that you had like a triplet sitting next to a quartet, and they have chemical shifts that are pretty close. Well, what you know is, you know that the chemical shift function of magnetic field. So if this peak is at 1.0 parts per million and this is at 1.1 parts per million, that's never going to change if you go to a stronger or weaker field. But what will happen is this. The distance between these two peaks will change. So while the parts per million value doesn't change, the hertz will. So if there's a difference of 100 hertz between those two peaks, if you go to a magnet that's twice as big, then it'll be 200 hertz. Or if you go to a magnet that's half as big, it'll drop down to 50 hertz. So what we're talking about here is the distance between the two peaks, not in chemical shift, but in hertz. So what happens is if these two peaks become close enough where their distance between each other in hertz gets close to being the coupling constant. Okay, let's say there's a 30 hertz difference between the two peaks. Constant is like 7 hertz between all the peaks. The spectrum is no longer first order. It's no longer simple triplet and quartet. Instead, it becomes a mess. And that's what's called a non-first order spectrum. Okay, so that's what I'm looking at. And I can vary the distance between the peaks by changing the field. I can't change. So in this case, here's what happens. We'll start with the issue of this is isopenyl or isopentane. And these two peaks are the coupling patterns that you would predict, the CH and the CH2. So in this case, if I call the CH A and I call the CH2 B, this would be the A splitting pattern and this would be the B splitting pattern. Okay, the hydrogen has 3, 6, 8 neighbors, and the B has 3 plus 1, it's got 4 neighbors. It would be a 9-peak pattern and a 5-peak pattern, and that pretty much matches up. But what you can see is you have nice, clean patterns. But the chemical shift difference here is pretty small. This spectrum only goes from 1 to 2 parts per million. So this peak is about 1.7 and the other one's probably about 1.5. So they're really, really close. This is what we would predict if we have a very large magnetic field. In this case, this is what you would get if you took the spectrum on a 360 megahertz instrument, just like the one we have next door. But if I was to take this on an older 60 megahertz instrument, where the magnetic field is only 1/6, what would happen is that these peaks now would have less hertz difference between the two. Chemical shift would be the same, but the hertz difference would be less. And if that becomes, again, if the distance between the peaks becomes approximately the same as the coupling constant, you don't get a nice spectrum like this. Instead, you get like this. And so once those two peaks get so close together that their distance is roughly the same as the coupling constant, the spectrum is no longer predictable. It's not first order, it's what we call a second order or a non-first order spectrum. Okay? So this is much older 60 megahertz instrument. This would have been the pattern. There's no way we can interpret that pattern. If we look at those peaks, we don't even know necessarily that that's one or two or three sets of peaks, because it doesn't fit our rules about doublets, triplets, quartets. So one of the reasons why we spend $10 million on an NMR magnet is because we want to try and separate the peaks as much as possible in hertz. I can't do anything about the coupling constant. The coupling constant's fixed. But I can try and use a bigger and bigger magnet to make differences as large as possible in hertz, and once I can separate those peaks out, they'll return to their first order spectrum. You may say, who cares? Well, people that study molecules that have lots of hydrogens, that have really small chemical shift differences, they care about that kind of stuff. Who are they? Study proteins, where there's thousands of protons in a very small window of chemical shift. Polymers, which are long-chained molecules. And so the reason that CASE and the Cleveland Clinic and the Structural Center for Biology has that humongous 900 magnet is because they're studying biomolecules where they want to separate these people. They can't do anything productive with this, but they can try and figure out the structures if the peaks are at least separated and they show their normal coupling patterns. Okay? And so that's why we spend all the money on having big magnets, is to overcome this non-first order issue. So that's a limitation to coupling. And that's, while it's not something that you necessarily have to worry about, it is something that other people have to worry about when they have lots of hydrogens that don't vary much in chemical shift. And that's why you see some of these 900 megahertz magnets, or if somebody has over one whatever it would be magnet, then that's why they're doing it. Because this doesn't tell me anything. Now, unfortunately, when I took spectroscopy as an undergraduate, it was its own separate course. It wasn't in the lab, it wasn't in the lecture, it was like its own separate course with its own not so good grade. This is the kind of stuff we had to look at. No wonder why I didn't learn it very well, because it just didn't make any sense. Then we used to try and compare our unknown compounds to books that had spectra in it. And we actually had these books up until about 5 years ago. It was a whole bookshelf just full of pages and pages and pages of spectra, but they were all taken at 60 megahertz. So when we moved to the new building, it's like these, because the 60 megahertz spectra, while the chemical shifts are the same, the appearances aren't. And so they all went somewhere, but they didn't come with us. So that's a limitation, is the fact that, yeah, chemical shifts don't change over time, but with stronger magnetic fields, your spectra, which you can interpret. So that's one of the reasons why people want to get higher and higher magnetic fields. So that's a complication, what we call a complication to splitting. There's another complication to splitting, and that is hydrogen exchange. So far, when we've talked about splitting patterns, we've only dealt with hydrogens attached to carbon. Why haven't we done anything with hydrogens attached to oxygen or nitrogen? Because they exchange. Imagine that you had an alcohol. So if I put an alcohol, it would look something like this. You know, you're going to have your first alcohol molecule, and then you're probably going to have another alcohol molecule come in and at least maybe hydrogen bond to the first one. Well, if you have two alcohols and they come in and they form that looks something like that, when they break apart, there's no guarantee that, let's call this a square oxygen and a square hydrogen, and we'll put a triangle on this. So there's no guarantee that the square hydrogen, when these things break apart, goes back with the square oxygen. It could very easily end up, and the triangle hydrogen, when this molecule, this hydrogen bonded complex breaks apart, that hydrogen could end up with the square oxygen. So in the NMR time frame, in that snapshot that we take over the course of a couple seconds, if these molecules come together and hydrogen bond and then break apart and the hydrogens get all scrambled, predict the chemical shift. And so for alcohols, for amides and amines, well, not for amides, but for amines, NH, NH2s, and carboxylic acids, the chemical shift of the OH or the NH could be anywhere. It could be anywhere between 2 and 14, which is the working region of a proton spectrum. So that means these peaks could show up anywhere. They don't have defined chemical shifts. For a nice pure carboxylic acid that has no water in it, then that would end up about 12. But as soon as the solvent gets wetter, there's other issues, alcohol or water inches begin to scramble themselves, and so the chemical shift is unpredictable. So that's a problem. And what it means is that we really don't have a table for OHs and NHs. The chemical shift could be anywhere. And what it also then means is that if that hydrogen, that OH, is constantly being swapped out with another, that it can't split its neighbors. Because there's not, during the snapshot, it's not the same hydrogen sitting there. If multiple hydrogens come in and out, it doesn't split the neighbors. So if you have like a CH3, if you have methanol where you have CH3 and OH, because that hydrogen is constantly OHs in the same molecule, the CH3 here won't see it as a neighbor and it'll just be a single peak. So there's no coupling. So when we've defined coupling, we've only worried about hydrogens attached to carbons because they don't exchange. So these don't couple and they can show up anywhere in the spectrum. Now if you do end up with a peak, and you can see it, sometimes what happens is the peak gets really broad because of that exchange process. And sometimes that peak gets so broad that it just disappears in the baseline and you never see it. But if you do see an OH peak, whether or not it's OH, by adding D2O. So D2O is water that's been substituted with the deuterium, the isotope of hydrogen with a mass of 2. It turns out that every isotope of an element has a different Larmor frequency. So protons flip. It turns out that deuterium, because it's a different nucleus, it flips about 40-ish, somewhere in the 40 megahertz region. Well, my instrument is tuned so it's pulsing 300 megahertz and the receiver is collecting 300 megahertz. So anything else that's not 300 megahertz just doesn't show up. Solvents that have D in them, whether it's CdCl3 or D2O, there's no protons there, so you don't see the peaks. So in this case, what happens is if you add D2O to a sample that has OHs or carboxylic acids or amides, what the D2O does is it comes in, and then when it exchanges off for the hydrogen, the peak disappears. So sometimes if we end up with an OH peak in our spectrum and we want to confirm that it's OH, we add D2O to the sample, shake it, reacquire the spectrum, and if that peak disappeared, it was OH. So that's how we can tell that a peak is really an OH changeable. These three, just sort of relating this to lecture, these three things are the same three things that would be deprotonated by a Grignard. Right? When you make a Grignard reagent, you have to avoid certain things like alcohols, amines, and carboxylic acids. Same three things, because those hydrogens changed, or in that case, they're acidic. Okay? So that's a complication. So we're not going to do anything with OHs and NH2s. And when we do get to real spectra, if there's a broad peak and I put a little asterisk on it, I'll say this peak disappears with D2O. And that means it's an OH or an NH or carboxylic acid. That's why we don't worry about coupling, because it doesn't exist. All right. So if I'm really going to start looking at molecules and looking at their proton spectra and try and figure out what the structure is, I need a lot more than just the proton spectrum. I'm going to need, I'd like to have an infrared, I'd like to have a mass spec, but there are other NMR techniques that will help me. For instance, protons are not the only nucleus that we can do NMR with. As a matter of fact, we can do NMR on any nucleus that does not have an even number of protons and neutrons. As long as the nucleus does not have an even number of protons and neutrons, it has the possibility to do NMR. Sometimes you can do it, sometimes practically you can't. But one of the problems is this. Carbon is mostly carbon-12. It would be great to get the carbon and organic molecule. Because what's an organic molecule made of? Carbon and hydrogen. So if I could get a spectrum of both of the two major elements in an organic molecule, I can figure out its structure. But carbon-12 is 98.9% abundance of all the isotopes of carbon, and the problem protons, 6 neutrons, doesn't have an NMR signal. But there is an isotope of carbon called carbon-13, and while it's 1.1%, it has 7 neutrons and 6 protons and electrons. So it has a signal. And so a single scan to get a carbon spectrum, we have to take lots of scans and add up the signal over time, but eventually we'll see that 1.1% of the carbon-13 in our sample. It might take us 5 minutes, it might take us 5 hours. It might take us 15 hours, depending on the concentration. Look at each carbon then in the molecule. And that's the limitation. When I was an undergraduate, we couldn't do carbon because we had an instrument that did 1 scan. So you weren't seeing carbon-13. Okay? Didn't mean that those instruments didn't exist. It meant that we didn't have one. Now, our instrument next door, I can get a carbon 1 scan depending on how much stuff I have. But I could definitely get one in 5 minutes or an hour or 2 hours. Okay, so we can do more than just protons. So carbon-13 we'll talk a little bit about, and then over the next weeks we'll do a little more practical stuff with it. But there's other, just to show you some examples of some weird stuff that people have done. Phosphorus-31 is almost 100%. Almost all the phosphorus is in phosphorus-31 nuclei, and you can get an NMR spectrum of it as well. For instance, in Dr. Kwan's research, if they make a molecule that has a phosphorus in it, they like to take a spectrum to see if that chemical shift is where it should be, given the structure. If they have some impurities in there that have phosphorus in it, they want to make sure they just see one phosphorus peak and not that of the impurities. So there's lots of things. But in biochemistry, you can do phosphorus NMR to look at things that contain phosphorus, like energy molecules like ATP, or the other one, whatever it is, ADP or whatever. But this is like a 20-year-old spectrum where they basically took the leg muscle of a rabbit, and I think the rabbit was still in contact with its muscle. And what they did was they put the rabbit inside of a magnet, and then they had to coil to the skin. That basically, that's how it applied the radio frequency, and it had the detector and everything in it. And I'm assuming in this case they made the muscle flex back and forth so that they could watch the different forms of the ATP come and go to try and study the energy metabolism that occurs within a muscle. I've heard of them doing that with people, putting your arm inside of the magnet and then putting a surface coil and having people flex back and forth to see how the energy changes occur within the phosphorus molecules. That's what they were doing apparently with this rabbit. You could say, well, did they stick the little rabbit down our little R2D2 magnet? No, because it's only this big. But, it's because they stick people inside of them to do MRI. And when you have an MRI done, basically what you're doing is you're mapping out the density of protons in the body, okay, by techniques that aren't quite the same as what we do in the lab, in our lab. But that's what they're doing. They're mapping of protons. Well, where are those protons coming from? Water. What's most of the soft tissue made of? Water. And so they're imaging the soft tissue by imaging the concentration of water within the body. So that's how they get a picture of your brain or your knee or whatever they're doing. It's the same thing. After break, there's a little sheet that I got from the plane dealer one time. They explained how MRI works to high school athletes. That's pretty good. It's actually surprising how much we've talked about showed up in that article. But there's other elements that people want to do MRI on. And so you can do other elements like phosphorus. You can do, for biochemistry, proteins have nitrogen in them. So they want to do N15 NMR to try and figure out the structure of a protein. Because if you figure you got hydrogen, carbon, and nitrogen, those are the three big elements that are in a protein. So you can do other elements, but these are kind of specialized, and they're not the easiest thing to do necessarily. So this is just an example. I have seen worms stuck in an NMR tube and stuck in the NMR. When I was a postdoc at Brown, one of the groups did something with worms, and then the worms would escape the lab, and you'd see a worm crawling up the hallway, and you'd have to go get the person for them to come and retrieve it, or it would just be a stray wilding that probably then volunteered for some sort of experiment. But the worms never died. When I was at Duke, they did something with turtle hearts, and unfortunately the turtle couldn't go into the magnet, only the heart of the turtle. And they hooked it up to an EKG machine to make it beat while it was inside of the magnet. So people do some probably pre-MRI days. So they were doing MRI with basically the instrument that we have next door. So you can do different things. You don't just do carbon and hydrogen, but that's what we're going to talk about. So in the carbon-13 then, basically, carbon-13 is only 1.1%. We've got to take lots of scans and add up the signal. Where there's just noise is random, so it cancels out. But where there's signal, the signal adds on top of each other, and you get a bigger and bigger peak over time. So it's just time intensive. And we do that by Fourier transform NMR, which is beyond the scope of what I want to talk about. In terms of coupling, though, and we'll talk more about this, we'll talk a little bit about it today, but we'll talk more about it in the future. If you think about neighbor coupling, it doesn't happen. It'd actually be nice to have it happen, but it doesn't. Because if you think about the probability of having a carbon-13 nucleus is 1 out of 100. And so the probability of having two C13s next to each other is going to be 1 in 10,000. When you figure the probability of each carbon is 1 in 100. If we could tell how many carbons were attached to each other, oh, that's a carbon with 2 other carbons attached to it, but we can get that information other ways. So carbon-carbon coupling doesn't occur, although there are some tricky experiments you can do to get this information. Now, what carbon does couple to? So if you have a carbon attached to a hydrogen, you will actually see the carbon split by its attached hydrogens. And that rule is n+1. And what gets confusing is that we've now learned that n+1 equals the number of neighbors. Well, in carbon-13 spectra, n attached hydrogens. So that means that if you had a CH, it would be a doublet. If you had a CH2, it would be a triplet, and if you had a CH3, it would be a quartet. And after that, you can't have like 5 hydrogens attached to a carbon. Well, you can, but that kind of violates that won the Nobel Prize, and he only made CH5+. So in a normal molecule, you're not going to have anything more than 3 hydrogens attached to a carbon. So you're going to have quartets, triplets, doublets, and singlets. And so that's an issue. And I'll show you in a minute that actually can be used to figure out the pieces. The other thing that's important is that the chemical shift of the carbon is going to tell us about its environment. So we're going to have regions where we find benzene ring carbons. We're going to have regions where we find carbons attached to oxygen. We're going to have a region of the spectrum where we find just run-of-the-mill alkanes. And so just like in proton, the chemical shift tells the kind of hydrogen you have, same thing's true for carbon. And what we find with carbon spectra is that I think I got rid of these in your handout. What turns out to be different for carbon is this. The chemical shift scale isn't just 0 to 12, it's 0 to 250. So it's a much bigger scale, which means that the carbon peaks are going to be separated. Very rarely do you have a lot of overlapping carbons for small molecules. So that means each peak is going to tell you how many uniques you have in the spectrum. You figure out the number of unique carbons exactly the same way you figure out the hydrogens. Could I have a mirror plane? Are they rotationally equivalent? All of that. So what you can do is you can count up the number of carbons and say, oh, I have 5 unique carbons in my molecule. Well, my structure better have 5 unique carbons in it. The hydrogens may be different number there. So we've got a bigger chemical shift scale. Our reference is still TMS. Only in this case, it's the carbon of the 4 CH3s. That's our reference. So we set that at 0. So here's a couple of carbon-13 spectra for 2-butanone. If you look at 2-butanone, 1, 2, 3, 4 unique carbons. Okay, now what's new is the carbonyl shows up because I'm looking at the carbon spectrum, not the proton spectrum. The proton spectrum of this molecule would just have 3 sets of hydrogens, but the carbon has 4. And if I use the rule, and on top, this is what's called an undecoupled spectrum, but here's a singlet. What does that mean? Well, a single carbon peak means it has no attached hydrogens. And its chemical shift is in the 200 to 220 part per million region, and we'll find out on a chart that that's where carbonyl show. So this peak turns out to be our carbonyl because it's just a single peak and it has the right chemical shift for a carbonyl. If you look at some of the other ones, then if you look at the last 3, what we've got is we've got a triplet and 2 quartets in that top spectrum. One rule says that if you got a triplet, that means you have a CH2. If you've got a quartet, it means you've got a CH3. So the power of carbon NMR is that it gives you the pieces. If you were able to get what's called an undecoupled spectrum, it would tell you that I have a C double bond O. I've got a CH2 because this is a triplet, and I've got two CH3s because they're quartets. And so then it's my job just to put the pieces together. Well, what do I use to put the pieces together? Proton spectrum, because a CH3 sitting next to a CH2 is going to be a triplet and a quartet in the proton spectrum. So the proton spectra tells me how to put the pieces together. The carbon tells me what the pieces are. And so we really need both. If somebody just walks up to you and gives you a molecule, but it could, in theory, sometimes that happens in forensic labs if they get something that isn't in their database and they want to know what the structure is. Or if you go through all the trouble of stripping the bark off the California yew tree and you find out that you have an anti-tumor drug and you need to know what its structure is, you're going to need more than just a proton spectrum. So the carbon will help give you and then the proton will help put it together. And the infrared will tell you whether there's an OH or a carbonyl or all the other stuff in it. So that's what we use this undecoupled spectrum for, is for the, basically for identifying the pieces. The limitation on this is that if it took me thousands of scans to get a signal, then if that signal, that small signal, all of a sudden gets split up into 4 signals, those 4 signals become really small. So most of the time we actually don't run undecoupled, we run what's called decoupled, and we actually could all explain that later. But the idea is that the carbon gives us, can give us the pieces. And then, if you now look at a chart, there are now charts where you can determine what the chemical shift of the molecule is and what kind of carbon it is. For instance, carbonyls show up anywhere from about 160 to 220. Double bonded carbons, whether they're in an aromatic ring or whether they're just alkenes, show up between about 120 and 140. Carbons that are attached to oxygens are in the 60 to 70 to 80 region. Run-of-the-mill CH2s and CH3, the 10 to 20 parts per million region. So just like for protons, there's a chemical shift scale for carbons, and so you can look at the position of the peak and say, oh, this molecule has a carbon that's attached to oxygen. But I can do better than that because I can say that carbon is a CH2 or a CH3 or a CH, and so I can tell alcohol or a secondary alcohol or a tertiary alcohol. I can do the same thing for the halogens. Okay, so we're really going to need all the pieces of information to put them together to figure out what the structure is. And we're just going to touch upon the techniques that people use, but it's possible to take a molecule that has 20 take the assignments of all the protons and the carbons and figure out the structure. But we're going to just talk about the basics. So we need more information in order for somebody to just say, here's a proton spectrum. Tell me what the structure is. If we have a carbon to go with it, we're going to be better off. If we have an infrared to go with that, mass spec. The mass spec will give us the formula which will tell us how many parts we have. So we're going to start putting everything together here towards, for the rest of the semester and start solving problems where I just give you all this information and say, okay, what's the compound? And that may seem fascinating, but if we follow a sort of systematic way of doing it, then it'll make sense. So we're not going to do any homework problems for this problem. So the only homework problems then are the ones that are due by tomorrow night.